9.1 is on sequences and series. Okay, so here we have an infinite sequence. It's just a list of terms that have an order to them. Because it's infinite, it goes on forever. So there's a first term, a second term, a third term, and there's infinitely many terms following it. A finite sequence has a first term and a next term, but then there's also a last term. Whether that's 10 terms, 20 terms, or a billion terms, it has to be finite. Okay, so for example, one, we're just going to find the first 4 terms of the sequence as defined by this formula. And we assume that we are going to start with the first term on all these sequences unless otherwise indicated. Okay, so if I want to find the first term, I indicate that is A1. So n is 1, so negative 1 to the 1 plus 5, which is negative 1 plus 5 is 4. So the first term is 4. 4 terms. So the second term, negative 1 squared is positive 1 plus 5 is 6. Now I want the third term. Negative 1 to the third is negative 1. Negative 1 plus 5 is 4. Fourth term. Negative 1 to the fourth is positive 1. Positive 1 plus 5 is 6. So the first term is 4. The second term is 6. The third term is 4. The fourth term is 6. I could continue from there. I can tell it's going to go 4, 6, 4, 6, 4, 6 forever, but they only asked for the first 4 terms. Okay, I'm going to do the same thing for B. B says A sub n is n over n factorial. I did briefly show you what factorial is in class, but I'm going to define it if you've never seen it. Okay, n exclamation point. In math, we say n factorial. Okay, n exclamation point is n factorial. So for example, if I do 4 factorial, which I write as 4 exclamation mark, I am multiplying the number 4 times the integer lower times the whole number lower, 4 times 3 times 2 times 1, so total, which is 24. So 4 factorial is 24. If I wanted to do 10 factorial, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Special cases, if I do 1 factorial, it's 1. If I do 0 factorial, that is also 1. Okay. We are going to use factorial in this unit, but just keep in mind 4 factorial, 4 times 3 times 2 times 1. And your calculator often has a factorial button, which I will help you find in class, hopefully. Okay, so anyways, let's evaluate this one. Okay, so first 4 terms, I'm going to assume the first term is 1, and I will always assume the first term is 1. This is 1 over 1 factorial, which is 1 over 1. So the first term is just 1. Okay, for the second term, n over n factorial. So 2 over 2 factorial is 2 times 1. If I cancel out the 2's, I'm just left with 1. So the next term happens to also be 1. Okay, for the third term, 3 over 3 factorial. 3 over 3 factorial is 3 times 2 times 1. The 3's cancel, so I'm left with 1 over 2. And for the fourth term, I have n 4 over 4 factorial, which is 4 over 4 times 3 times 2 times 1. The 4's cancel, and I'm left with 1 over 3 times 2 times 1 is 6. Okay, so the first term is 1, second term is 1, third term is 1/2, the fourth term is 1/6, and I could keep going from there to find subsequent terms. Okay, on the previous example, we defined the terms of the sequence by using a formula. We can also define them recursively, or by calling the next term based on the previous term. You sometimes use this in computer science as well. So this is going to be a recursive sequence. I want to find the next 3 terms after the one that is given to me. Okay, so let me see what they give to me. Okay, so they tell me that A1 is 5. So I already have the first term. I need to find the next 3 terms. Okay, and then they tell me this rule. They tell me a k plus 1 equals 3 times ak plus 2. Okay, so let me think about what this means. Okay, the only term they gave me is the first term. Okay, so let me think. If I want to find a to the 1 plus 1, and I picked k as 1 because I know what a1 is. According to this rule, that would be 3 times a1 plus 2. Okay, now I know that a1 is 5 because it was given to me in the given. So this is saying 3 times 5 plus 2 would give me the next term, which is 15 plus 2. That's 7. Okay, now why did I even care what a sub 1 plus 1 is? That's because a1 plus 1 is actually a2. Okay, so what the formula, now that we've plugged it in, what the formula is saying is if I want to find the second term, I do 3 times the previous term, and then I add 2. And if I want to find the next term, I do 3 times the previous term, and then I add 2. Okay, so I'm going to do it for the next one. I'll skip a step a little bit. So let's say I found the one term. I want to find another term. Okay, if I want the third term, I'm going to do 3 times the previous term, which was a2, and then I'm going to add 2. Okay, now the previous term I just found on my last step to be 17. Add 2. 3 times 17 is 51, plus 2 is 53. Okay, that's the next term. I want to find one more term because that's what the directions told me to do. Okay, so if I want the fourth term, I do 3 times the previous term plus 2. Okay, the previous term I just found to be 53. And then I'm going to add 2 to that. So what is that? 159 plus 2 is 161. Okay, this is called recursive because it's calling the previous term in order to get the next term. And I could continue this infinitely to find all the terms in the sequence forever and ever and ever. Okay, now the most famous recursive sequence arguably is the Fibonacci sequence. Okay, so this is how the Fibonacci sequence is defined, and it is a recursive sequence. Okay, so they tell you A0 is 1, A1 is 1. Now if I want to find AK, that's going to equal AK minus 2 plus AK minus 1. So if I want this term, I need to do the term that's 2 previous plus the term that's 1 previous. Okay, let me write this out, and then we're going to actually try to find the next 3 terms. Okay, so I have the 0th term, first term. I want the second term. Okay, so I want the second term. Okay, according to this rule, that's going to equal 2 minus 2. That's going to equal the 0th term plus 2 minus 1, the first term. Okay, now from my given above, I know that the 0th term is 1 and the first term is 1. So this is going to be 1 plus 1. So the second term is 2. Okay, now if I want the next term, I want the next 3 terms. Okay, now k is 3. 3 minus 2 is 1, so I want the second previous term. And then 3 minus 1 is 2. That's the first previous term. So now the A3 equals A1 plus A2. Okay, A1 was given to me. A2 I just calculated on the previous step. Okay, now for the fourth term, 4 minus 2 means A2. 4 minus 1 means A3. So I'm adding the 2 previous terms. Okay, for A2, I got 2. For A3, I got 3, which equals 5. Okay, and if I wanted the next term, I could add up the previous. If I wanted A5, I could do A4 plus A3. Okay, that's a recursive sequence because it defines the next sequence based on the previous term or terms. Okay, next we're going to go over what they call summation notation. This is also called sigma notation, and it's called sigma notation because this weird E thing is actually a Greek letter, and it's called the letter sigma, capital sigma. Okay, so summation notation or sigma notation. Okay, summation notation just means you're going to sum up a bunch of terms, or you're going to add them up. So this is the formula they're giving me for whatever term it is. Okay, they want me to sum the terms starting from here all the way up to here. So in this case, they're saying start with term 1, go all the way to term n, and then this sigma tells me to add them up. So a1 plus a2 plus all the way up to an, and then I add up all those terms. Okay. So if I look at this summation notation, they gave me this formula here, and they want me to add up all the terms starting with I equals 2 and going up to when I equals 4. So I'll plug in I equals 2, I equals 3, and I equals 4. And then because it's summation, I will add it up. Okay, so I'm going to first plug in the 2. 5 times 2. Okay, then what? 5 times 3 plus, and then I'm going to stop when I get to 4, plus 5 times 4. Okay, I plugged in 2 through 4, and then I just have to add it up because that's what summation is. 10 plus 15. Okay, so the resultant of this is 45. Okay, for B, I'm going to do the same thing. They gave me a formula. They want me to start with I equals 0 and add up all the terms until I get to I equals 3. So I'm going to plug in I equals 0, I equals 1, I equals 2, and I equals 3. Then I'm going to add all those results together. Okay, so let me start out by plugging in 0, plug in 1, plug in 2, plug in 3, then that's the last term I'm going to add up. These often, I'm going to say converge. So we're going to get an exact answer as a fraction. What's my common denominator? 1, 2, 3, 4, 12. So 12 over 12, 6 over 12, 12. So this adds up to 25 over 12, and that is the best simplification I'm going to do. Okay, the last word is series, because this was sequences and series. All series really means is that it's the sum of a finite or infinite sequence. So when they say series, it means you're going to add it up. And it's normally an infinite sum, but they can make you do a partial sum as well. Okay, so here's the series I'm given. And again, they're just saying series because it has the summation notation. I equals 1 to infinity of 4 over 10 to the I. This is an infinite series because it does go up to infinity. Okay, so for A, it tells me to find the fifth partial sum. So when I say fifth partial sum, it means they don't want me to do the entire infinite sum. They want me to stop when I get to I equals 5. Oh, I spelled fifth wrong. And I don't even think I'm going to change it. Okay, so let me set this up. Okay, so I'm still going to start at I equals 1, but because I only want the fifth partial sum, I'm going to stop at 5. Okay, so let me plug in 1. If I plug in 2, that's 10 squared. If I plug in 3, that's 1,000. If I plug in 4, that's 10,000. If I plug in 5, that's 100,000. Okay, now let me look at this. I think I'm actually going to make these decimals because they're terminating decimals. So I am going to get an exact answer. And because it makes a nice pattern that I'm going to reference in the next one. Okay, you will give an exact answer for these unless they tell you specifically to round to the nearest something, which they will sometimes. 1, 2, 3, 4, and then 4. Okay, if I add these up, I get 0.1. I get 5 fours. Okay, so the fifth partial sum of that series is 0.44444. Okay, now when they say find the sum of this series, now they're talking about they want you to find the infinite sum. So they want you to add up all the terms to infinity. And when they say that, that normally means they're going to be some sort of pattern because you can't actually keep adding until you get to infinity. Okay, now I'm going to consider the pattern that we started from above because it was a pattern that I could see forming. Okay, so when I only did the fifth partial sum, I did 0.4 plus 0.04 plus 0.004 plus, and I kept going forever and ever and ever. Now, because I only did the fifth partial sum, I ended up only having 1, 2, 3, 4, 5 fours in my answer. Now, if I had done the infinite sum and this pattern had continued, it would have been 0.444, infinitely long and infinitely repeating. Now, I'm going to rewrite this as a fraction. Okay, if you have not learned about repeating decimals, 0.4 repeating is actually 4/9. 0.5 repeating is actually 5/9. If I do 0.7 repeating, that's 7/9. I will leave you to ponder 0.9 repeating. I'm going to prove to you that 0.4 repeating is 4/9. You don't have to write this down and you can stop the video if you would like. Okay, but for your fun information, okay, this is how you prove that 0.44444 is actually 4/9. Okay, so I'm going to assume that n equals 4/9. No, n equals 0.4 repeating. Okay, I'm going to multiply this by 10. You don't know why I'm doing it, but I'm doing it for a reason. If I do 10 times n, I get 4.444 repeating, repeating, repeating. Okay, I'm going to list n under this, which is 0.444 repeating forever. Okay, then what am I going to do? I'm going to subtract these. Okay, now if I subtract this, 10n minus n is 9n. 4.4444 forever minus 0.444 forever gives me 4, which gives me n equals 4/9, which means that 4/9 in fact does equal to this. Okay, and that's just for fun information. Okay, if you have a repeating number like 0.13 repeating, I use the bar to represent repeating, I would rewrite that as 13/99. It has 2 digits repeating, so it's going to be over 99. And I would do a similar process to prove it, but I would do 100n minus n, and I would get this formula. Okay, so anyways, if you have any more fun facts about repeating numbers, look them up. And do ponder 0.9 and 99.